Cool.
Right. Hello, everyone. So just a disclaimer in the beginning. I didn't prepare slides. I wanted to sort of keep it a little bit more of a conversation in two ways, like just asking for some interactions with the people in the audience and just discussing a little bit about what we're doing at World with cryptography and in general, like how do we actually build privacy-preserving systems at scale. So first, I would like to ask you a show of hands. How many of you have heard of zero-knowledge cryptography before? How many of you feel like they understand ZK somewhat or have worked with ZK? Okay, that's good. That's more than I thought. Okay. So I'll introduce some of the concepts in a high level, and then I'll also go into some of the more nuanced topics for those who are curious and those who are more technical in the audience. So to start, I want to introduce sort of like what we do at World, formerly known as WorldCoin. Maybe you remember that name. So World is building a network for real humans. And what that means is that we're trying to bring accessible digital finance and digital identity to everyone in the world. However, with the sort of crypto ethos in mind, right? You want to bring sovereign digital finance the way that Ethereum envisions it, and digital identity in the way that sort of privacy-preserving, sort of cryptography-based systems allow you to do so. Because if you have finance in a way that is not self-sovereign, you end up with what we have already, which doesn't work at scale, and there's a lot of problems with that, as we know. And with digital identity, we also don't want to end up in a dystopian environment where all of our identities are public and we can get monitored by governments, et cetera, and all of that. So World has these values in mind. So when we're trying to build something at scale, these are the constraints that we're operating within. We want the user to have control over their finances, but we'll also want to give them accessibility to everyone in the world. So you need to make all these systems that we've been building in Ethereum and the L2 scalability systems and all these really sophisticated things. You want to give them to the user and make them accessible. A lot of the systems that we're building are like really sophisticated and the user experience is not that great. And so I would say that World is sort of a tale of a product driving technological innovation, where if you actually want to make it available to the user, there's a lot of things that permeate into the technical design of things that some other systems that have not reached scale don't really have to think about. Like we've seen in early Ethereum designs or like early privacy or digital identity systems. There's a lot of cool protocols, there's a lot of cool ideas and theories, but when you actually put it to the test, you see that these things actually are not runnable at the target audience that we want, which is the entire world. So what we have currently is a set of products. One is World App, which is the sort of hub for all things World, where the user downloads this application on Android or iOS, and they're able to interact with their World App wallet, and they're also able to interact with World ID, which is the identity protocol that we built. World App and all of the user wallets essentially are a safe smart account, and all of those live on World Chain, which is an OP Stack L2 part of the superchain. And World ID, the way it works currently, is that we have a prover, a ZK prover, that lives on the app of the user. And this is creating semaphore proofs. Semaphore is a protocol that was developed by the Privacy Scaling Explorations Group at the Ethereum Foundation, which we really are appreciative of because they helped us build a lot of things early on. And what this protocol allows you to do is that I'm able to prove that I'm a member of a set without revealing which member in the set I am. In the case of proof of personhood, which is what World ID allows you to do, it's essentially proving that I own a private key to a public key in a Merkle tree without revealing which public key I own. And this Merkle tree only has public keys of users that have been verified by the orb, which is a hardware device that we manufacture. Maybe you saw it yesterday. I brought one yesterday downstairs. So this orb essentially verifies the iris code pattern, which is just as like some representation of the randomness of the iris of the person. And this is also encrypted in MPC, so none of it is public. All of it is encrypted in private. We've worked with partners like Tasio, who are here today, and some other partners as well on getting this shipped to production. And so essentially, it's a privacy-preserving way of bringing a proof of personhood sort of attestation to many, many users. How many users, you might ask? Well, World App currently has about 23 million downloads. We crossed that number yesterday, or I think maybe the day before. So 23 million downloads across iOS and Android, and about like 10.5 million users have been verified by the orb. So 10.5 million users have a private key that can create a zero-knowledge proof. They can create a zero-knowledge proof of that they're members of this unique set of humans that have been verified by the orb. So now if you look at the sort of demographics or some of the like distributions of these world app users, well, they're not all in Europe, right, or in America, where people have flagship phones or like modern phones that have like lots of RAM, they have lots of memory, they have a good CPU, maybe sometimes even acceleration devices like GPUs or some like specialized hardware for doing specific things you can tap into. And so oftentimes you find yourself working with devices, mobile devices in our case, which are underpowered, or essentially they're like old phones from like 2013, which have like 2 gigs of RAM. 1 gig of RAM is consumed by the operating system, and so you only have like 1 gig of RAM of memory you can work with, which is very little. And you also have limited bandwidth for downloads and uploads, and so many other constraints. So when the user is downloading the World app, they also cannot afford to download like a 200 megabyte application, because maybe that's like half of their mobile plan for the month. And so when they're creating, for example, these proofs, the proofs cannot be big, they need to be small, they need to be accessible, yada, yada. So when you're working within these sets of constraints, it sort of pushes you to innovate, because the existing focus in the zero-knowledge space has mostly come from things like rollups and scalability solutions, where all of this data is public, hence you don't really need ZK, you don't need zero-knowledge. This is sort of like the great misnomer of our space, where we call everything ZK, but sometimes we just mean snarks or starks, not ZK snarks, ZK starks. We don't mean privacy, we just mean I'm able to create a computational proof of integrity of some computation happening. And so when you actually need ZK, you need to have the witness, the private data you're making, the public and private data that you're making a proof of, you actually need it to be at the client. You need to have that data where the proof is happening. And if that data is private, you don't want to put that data in a server, right? Because if I want to make a proof about my identity, I want to give my identity data to a server to create that proof of that data, right? And so these are sort of like the fundamental sets of constraints that we have if you actually want to have true privacy. So what we have currently is the semaphore protocol, and semaphore, for those who are technical, essentially you have a Merkle tree of Poseidon hashes, because Poseidon is a friendly hash function for ZK systems, and it's just a Gross-16 proof. It's a Circom circuit, it's written in Circom, and we're using ArcWorks, the Arc Circom backend, which just compiles to ARM, and that ARM binary runs in the World app. And you're able to have a custom witness generator and just runs a client-side performant proof. And even in low-end devices of the distribution of 24 million users, that proof happens in less than a second, because the circuit for semaphore specifically is like about 20,000 gates or 20,000 constraints. It's not that much, so it's quite simple to create a proof of. But if you move into the wider spectrum of identity and what we want to have in the future of identity, we want to create general programmable predicates about your identity. We don't want to just create a proof of personhood, but you also want to create a proof of maybe like I'm over 18, or I want to create a proof that, like maybe you've heard of web proofs, right? I want to create a proof that I've done more than 10 rides in Uber, or I've bought more than $100 worth of this Adidas store, or I've done any X things on the web. Or also on-chain, right, with storage proofs. I can create a proof that my balance on this wallet is greater than X. Or I've interacted with Aave more than 100 times. My collateralization ratio is over whatever. So these are sort of the whole realm of your identity that is fully sort of available to you, but right now there's no ways to actually create proofs about that in a privacy-preserving way. If you want to create this proof, you usually are constrained to like server-side provers that are really performant, and you cannot really create the proof at the client. And so what we want to do is invert this on its head and create a performant client-side prover that is able to allow you to do arbitrary statements, arbitrary predicates, arbitrary proofs about your identity, all in your mobile device. And when you're working within the constraints of a mobile device, and with the user base that we have, with the tail-end distribution of all the users that have mobile phones, that have World app installed, you have to make this performing client-side prover performant even on low-end devices, so that it's accessible to the world, pun intended. So in this case, what we've been doing is over the last sort of half a year, we've been contacting a bunch of different partners who are interested in working on client-side proving. One of them, I don't know if I see Giacomo in the room, but for example, one of them is here, Giacomo Fenzi, who created the WIR paper. For those who are technical, I'm now going to go into a little bit of the more technical side of things. Currently, we're using Graph16, right? Graph16 is great because on-chain, it's easy to verify on-chain, but the problems with Graph16 are several. One is that you have a trusted setup, meaning that the prover needs to have the trusted setup files in the phone. For Semaphore, the trusted setup file is quite small because you only have like 20,000 constraints. So it's 2 to the, I forget like what the power of 2 to get over 20,000 constraints, so that you have a trusted setup for the bigger circuit that is. But it's quite small for a tree depth 30. So you have like 1 billion identities in the Merkle tree. And so the problem is that if you actually want to create a proof of a large circuit, a large attestation, a large statement about your identity, that number of constraints is going to grow a lot. It's going to be in the order of like 2 million, 4 million constraints, like 2 to the 23, 2 to the 24 constraints. And so you want to make proofs of something that is that big, like from 1 million to 10 million to maybe like 20 million constraints, because with that you can already make sophisticated proofs about your identity. Because oftentimes the credentials you work with are, for example, passports. I presume most of you have a passport. I don't think I need to ask that question. And in your passports, most modern passports, I presume most of you have a digitally enabled passport, which has this cool logo in the bottom with this, like, oh, it's a digitally enabled fingerprint passport. And so what that passport essentially has is that all of the information that is written in the front page is actually written in the NFC chip itself, and that data is hashed and signed by the issuing authority. And the problem of these systems is that they were not made with zero knowledge in mind. All of these existing cryptographic systems that are in these sort of passports are sort of traditional cryptographic primitives, right? You have like RSA as a signature scheme and maybe like SHA as a hash function. And these are not ZK friendly, and the blow up factor is quite large, and hence you're going to grow the size of the circuit by a lot. So it's infeasible to do this. Hence you also need these client-side proving systems. So when you get to all of this, if you want to create a Graph16 proof of this, it's nearly impossible on a low-end device, because just to have the trusted setup files, the trusted setup files themselves would be like 200 megabytes. And you cannot download 200 megabytes for the World app just to create a proof of that, because then maybe you want to create another proof and then you have to download another 200 megabytes. So it just never scales. So you really need a transparent proving system. So this is something that we had in our sort of set of constraints. But then there's all other things, right? You need the proof time to be really fast. And for some things like hash-based schemes, some of those things are not quite friendly. And so what we ended up choosing is Spartan. Spartan is a proving system that came, I think in 2016, 2017, is one of the first ones. And it's a transparent proving system, so it doesn't need a trusted setup. And the cool thing is that it's really performant. However, the proof size is quite big. So if you want to make it succinct, it takes a long time of like lots of rounds. And so this is sort of something that we don't want. But the cool thing is that you get the properties of soundness and soundness and zero knowledge within just like one round of sum check, I think, and one commitment and one opening. So it's like you can get zero knowledge, which we care about. We want privacy at the client, and we want soundness, meaning that the proof is correct, and I cannot like fake a proof. That you can get that immediately, which is great. And so now that we have that, we can defer that later to a server to actually make it succinct and recurse it and make it actually small so you can verify it on chain. We can do that later. So what we ended up coming to, like end-to-end, or what we're working on right now with multiple different teams, is we're using Noir, which is a DSL built by the Aztec team. The reason for Noir is that Circom has outdated tooling, is hard to work with, and if you've ever worked with Circom code base, it's mostly just Jordi's JavaScript that he wrote in 2018, 2019, and it's really hard to work with. And Rust is just a better programming language all around because of memory safety and lots of other things. I don't need to nerd snipe you on Rust now, or maybe later. So essentially, we're using Noir because it's a really good developer experience, and it has an agnostic backend. You can just compile that to anything. OK, I have time still. So you can compile that to anything. So the cool thing is that we are creating a backend for Noir to target this Spartan prover. Spartan works with R1CS. And there's this other version of R1CS called GR1CS, which is this general R1CS instance. And you're able to compile Noir to GR1CS. And then from there, you're able to feed it to Spartan and you can create a Spartan-proof client-side. Another thing that we've been working on is an efficient interactive oracle proof. So you can do a commitment to the witness vector of polynomials that we have. And for that, we're using where. So where is a direct replacement for stir and fry. So where essentially, I'm not a cryptographer myself, but I understand sort of the high level. Where is a proving or an IOP that is like stir, but also takes some ideas from basefold, and it allows you to commit to multilinear polynomials really fast. And so Giacomo, who is somewhere around, either if not here, he's somewhere around the conference, is the author of that paper, and he's working with us on that. And he is, like, we're helping him build the performant implementation of this so we can use it ourselves. And it's fully open source, published on ePrint. I suggest you read that paper. So with Spartan and where, you're able to create a performant client-side proof that you can then work with later on the server side, because now you already have privacy and soundness. So let's recapitulate, right? We have Noir into GR1CS for the representation of the polymer constraints. GR1CS allows you to have custom gates and lookups, and it also allows you to have like polynomials that are not quadratic, like regular R1CS, like just more complex polynomials, which is good. And then you can feed that into Spartan, and with where as the IOP, it's sort of like the most performing client-side proof you can have. And this is what we have right now. The reason for Noir also is that there's a lot of performant implementations already in Noir of different protocols. Maybe like if you know Ayush or the ZK email team, they built a great protocol for creating proofs of email data, right? Like all of your emails are usually signed by some email key, which is an RSA signature usually, and you just verify this RSA signature, and then you can do this like ZK regex of your email data. So it's another part of the identity. So once you have all of that, you combine it with a recursive Groth16 prover. The reason for why we're still using Groth16 in the end is mostly because of legacy reasons of the EVM. It's still unbeatable because Groth16 has a constant size proof size, and it's just 8 field elements, BN254 field elements. So in the EVM, it translates to 8 words, like UN256 words. And you can also compress that to 4 with a cool blog post that Remco on our team wrote. So you can compress it to just 4 EVM words, which when it comes to like cold data consumption, if you want to submit hundreds of thousands or millions of these proofs like we do on WorldChain, you really need something that is small. And so this is why we're using still Groth16, because for legacy reasons where the EVM has a lot of constraints on verification, it only supports BN254 precompiles. And so that's why we're doing that. And also the constant cold data size, because WorldChain is already consuming a lot of blob data on Ethereum. And so you really want to minimize your footprint of how much data you consume on chain. So essentially, you take the Spartan proof, you recurse it with the general Groth16 circuit, and meaning you can, the reason why it's general is because you can recurse multiple Spartan proofs into one Groth16 proof, and the Groth16 prover will just have the maximum amount of the powers of tau for creating the maximum circuit size for the aggregation of all these Spartan proofs. And so once you have this like really efficient end-to-end system where you're able to go from a Noir circuit that allows you to make proofs about your identity. It might be semaphore, it might be ZK email, web proofs, storage proofs, this NFC ID proof of the passport data that you have, all of that client side. And from the benchmarks that we have, you're able to create these proofs in sub-minute in low-end devices, right? And sub-minute is already sort of like a user experience that is acceptable by the person that lives somewhere where they're not able to afford phones, right? It's still a trade-off. We'd like to make it faster, but it's just impossible with current technology. So these are sort of the constraints. Now back to the non-technical side of things. If you worked with real-world constraints, like we do, where we're operating in all 5 continents in the world, where there's users of all sorts, from all kinds, and if you want to actually support them and give them access to finance and identity, you need to make the systems and technologies you built actually usable by them on a technical level, but also on a user experience level. So these are sort of why I believe that working for the end user always ends up making the best technology, because you always factor in the real world constraints, and then you have the massive distribution and actual change that you can affect on the real world by actually allowing them to use that at scale. And then now you have fully privacy-preserving digital identity for all sorts of things that you can make proofs about in the hands of millions of people, which is what we've been here for all about in all of these years in Ethereum and other places as well. So this is what we've been building, and If you want to contact me, feel free to just grab me at the end or go to my Telegram or Twitter. It's dcbuild3r. Instead of dcbuilder, you just substitute that with a 3. I'm happy to talk to you anytime, and thank you for listening, and I hope you enjoyed it.
Thank you.